In this class, we are going to discuss about crystal lattice and unit cell. Crystal lattice means is the three-dimensional arrangement of constituent particles in a crystal is known as crystal lattice or space lattice. So it means the particles are arranged in a three-dimensional manner. Okay. There are only 14 three-dimensional lattice and it is named as Bravais lattice. Okay. In a crystal lattice, each point is called a lattice point or a lattice site. Each point represents one constituent particle. It may be atom, molecule or ion, and each points are joined by straight line to bring out the geometry of the lattice. So, this is an example of a crystal lattice. So, in this case, these points are called lattice point or lattice site, and each point represent atom, molecule or ion, and these points are joined by lines for what? To bring out the geometry of a lattice site. Okay. The next one is unit cell. It means it is the smallest repeating portion of the space lattice. So unit cell means it is the smallest repeating portion of a space lattice, and there are 7 types of basic unit cells, and those are cubic, tetragonal, orthorhombic or rhombic, monoclinic, trigonal, rhombohedral, hexagonal and triclinic. So in the case of cubic, the axial distance A equal to B equal to C. So the axial distance are same and the axial angles are also same. Then note the examples. Examples are ZNS, KCl, NaCl, Cu, etc. In the case of tetragonal, the two axes are same, but the three axial angles are 90 degree. The examples are SN, SnO2, TiO2, CaSO4. In the case of orthorhombic and monoclinic, the axial distance is not equal. Okay, note the examples also. Then in the case of trigonal and rhombohedral, the axial distances are same. Okay, note the examples. Then the triclinic, in the case of triclinic, the axial distances are not equal. All the axial distances are not equal. Okay, and similarly, all the axial angles are not equal to 90 degree. The example is CuSO4 5H2O. The next one is different types of unit cell. Okay, depending on the positions where the constituent particles are present, the unit cell can be classified into the following. So, depending on the position where the constituent particle present, it can be classified into 4. The first one is simple or primitive. So in this case, the particle occupy only at the corner of the unit cell. Look at the diagram. So the all particles are located at the corner. So it is called simple or primitive. Then the second one is body centered. It means the particles occupy at the corner and at the center of the unit cell. So the particles located at the corner and the center. So this type is called body centered. The next one is face centered. Face centered means particles occupy at the corner and the face of the unit cell. So particles are occupied in the corner. Look, then it is occupied in the face of the unit cell. So consider this face. So one constituent particle is here, and consider this face. One particle is here. So consider this one, and this particle is here. So 6 face contain 6 particles. Okay. Then in the case of n-centered, particles occupy at the corner and at the center of any two opposite faces of the unit cell. So particles occupy at the center and opposite face of the unit cell. It is called n-centered. Okay. So next we are going to discuss about the number of atoms in a unit cell. Okay. In three-dimensional lattice, a particle at the corner is shared by 8 other unit cells. Hence, the contribution of each particle is 1 by 8. So, we also seen that the particles occupied at the corner. Okay, if the particle occupied the corner is also shared by 8 other unit cell. So its a contribution of each particle in a unit cell is 1 by 8. So in a corner it is 1 by 8. Okay. Then particle at the face, particle present at the face center is shared between two unit cell and hence the contribution is half. Okay. If the particle is present at the face, then it has contribution to 2 unit cell. So that's why contribution of a 1 unit cell is half. Then the third one is the particle present within the body of the unit cell. So, okay, if the particle is present in the body, then it is not shared with the other unit cell. That's why its contribution is 1. So in body it is 1. Okay. The next one is a particle present at the edge of the unit cell is shared by 4 other unit cells and hence its contribution is 1 by 4. So if the particle is present at the edge, if a particle is present at the edge, it is contributed to 4 other unit cells. So its contribution to 1 unit cell is 1 by 4. So, okay, then we can conclude that at the corner is 1 by 8 and the face is 1 by 2, then body is 1 and the edge is 1 by 4. Based on this, we can calculate the particle number of particles in simple cubic. Okay. So in simple cubic, we already know that the particle is presented only at the corner. So there are 8 corners here and one particle's contribution is 1 by 8. So the number of particles is 1 by 8 into 8 equal to 1. And in the case of body centered, we already know that in body centered cubic, the particles were located at the corner and the center. So in the corner, we already know that 1 by 8 into 8. But in the body, it do not have contact with any other unit cell. So it is 1. Then 1 into 1 is equal to 1. So 1 plus 1 equal to 2. In the case of face-centered cubic, the number of particles is, so in the case of face-centered, and 8 into 8 is equal to 1. Then 6 particles are here and 1 particle's contribution is half. So that's why 6 into 1 by 2 is equal to 3. 1 plus 3 is equal to 4. So number of particles present in simple cubic is 1, in body centered is 2 and a face centered is 4. Okay, I hope you understand this topic. So the next one is close packed structure. It means during the formation of crystal, the constituent particles are closely packed. The stability of the crystal is depend on the extent of the close packing. So during the formation of crystal, the particles are closely packed. So in this case, we are discussing about the close packing in 1 dimension and in 2 dimension, 3 dimension, final in 3 dimension. Okay. The first one is close packing in 1 dimension. So in this case, we assume the particle as a sphere. So it means that the spheres are arranged in a row and touching with each other. So assuming the spheres are particles. So in 1 dimension, it is arranged in a row and touching with each other. Okay. And in the case of 2 dimension, it means the spheres are arranged side by side, touching each other in a row, and we can done in 2 ways. So it means we are arranging spheres in a like a plane. Okay, it is called the 2 dimension. So it can be arranged in 2 way. It means square close packing. The first one is square close packing and the other one is hexagonal close packing. So first we can discuss about square close packing. So square close packing means the spheres are arranged in such a way that the rows have both the horizontal and vertical alignment. So in this case, we arranged spheres in horizontal and vertical manner. Okay. And in this case, we can see that this sphere is surrounded by 1, 2, 3, 4. 4 spheres. Okay. This sphere is touched by 4 spheres. Okay. So it is like a square close packing. Okay, I hope you understand this. 1, 2, 3, 4. So it is like a square and it is called a square close packing. Okay, the next one is hexagonal close packing. And in this case, the spheres in the second row are placed in the depression between the spheres of the first row. So it means that we are arranged spheres in the first row, and in the second row we arrange spheres in this depression, okay, between these depressions, and we arranged here, okay, like this. And in this case, one sphere is touched by 1, 2, 3, 4, 5, 6, 6 other spheres. So it is like a hexagon. Look, it is like a hexagonal. So it is called the hexagonal close packing. The particles are more closely packed in hexagonal close packing. Okay. The vacant site in the close packed structure is called voids. So this is called a void. This is a vacant site in this close packing and it is called voids. And we can discuss there are two types of voids are here. The first one, these two are the voids presented in a crystal close packing. First one is tetrahedral void and the next one is octahedral voids. Okay. In a crystal having n particle, suppose if a crystal having n particle, then the number of octahedral void is n is equal to number of particle, and the number of tetrahedral voids is equal to 2n. Tetrahedral voids is twice the number of particles. Okay. Then the next one is close packing in 3 dimensions. So it means that first it is developed by retaining a two-dimensional hexagonal close packing in the first layer, and this layer is marked as capital A. A second layer is obtained by placing the sphere over the voids in the first layer. So here we are doing first we are retaining the two-dimensional layer, and above on which we are placing the second layer. So hence a three-dimensional layer is formed here. Okay. And in this three-dimensional layer, there is two type of voids are formed. The first one is tetrahedral voids and the second one is octahedral voids. If the spheres of the second layer is above the voids of the first layer, and if we are placing the second layer spheres above the voids of the first layer, then it is called a tetrahedral voids. Then octahedral voids means the triangular voids in the second layer is above the triangular voids in the first layer. Then it is called the octahedral voids. So in three-dimensional close packing, two type of voids are formed here. Then we can place the third layer by covering the tetrahedral voids and the octahedral voids. Then we can discuss that. So the first one is covering the tetrahedral voids, and in this case, when the third layer is placing above the tetrahedral voids, the alignment of first and the third layer became identical. So if we covering the tetrahedral voids, the first layer and the third layer became identical. So the pattern is AB AB, and the structure is called the hexagonal close packed, and the examples are magnesium, zinc, cadmium, and the figure is, so in this case this is our tetrahedral voids, and we are covering a third layer by covering this tetrahedral voids. Okay, and in this case a hexagonal close packed structure is formed, and the patterns of the layer is like AB AB type. Okay. And the next one is covering the octahedral voids. In this case, when the third layer is placing above the octahedral voids, a different arrangement is obtained. So when we are covering the octahedral voids, we get a different alignment or a different arrangement. So the first, fourth and seventh layers became identical, and the pattern is ABC, ABC, etc. And the structure is called cubic close packing or face centered cubic, FCC. Then the example is copper, nickel, gold. Then the diagram is, so here this is the octahedral void and we are placing a third layer by covering this octahedral void and we will get a cubic close packed structure or a FCC structure. Then the next one is coordination number. The number of nearest neighboring particle or a sphere in a crystal close packing is called a coordination number. Okay. So in the case of HCP and CCP, hexagonal close packing and cubic close packing, its coordination number is found to be 12. It means that 6 spheres in its own layer and 3 spheres above the layer and 3 spheres below the layer. So in the case of hexagonal close packing, the coordination number is found to be 12. The coordination number means the nearest neighboring particle in a crystal close pack. In both HCP and CCP, 74% of the available space is occupied by the spheres. In BCC close packing, only 68% of the sphere is occupied by the remaining space is vacant. Then the next one is packing efficiency. It means that the percentage of total space filled by the particle in a crystal lattice is known as packing efficiency. So packing efficiency equal to volume occupied by sphere into 100% divided by total volume of unit cell. In HCP and CCP it is found to be 74% and in BCC it is found to be 68%. In simple cubic it is 52.4. Okay, this is today's topic. Thank you, students.